I have been told that the best crackers in the world can do this in 60 minutes. Unfortunately, I need someone who can do it in 60 seconds.
You're kidding. Go!
This one is a very interesting case, where you are given 2 attempts to get the password right. This translates into a do while that will, most importantly, execute a vulnerable printf twice. This doesn't have to be the same vulnerable printf executed repeatedly, as it can just be another vulnerable one executed later down the execution path. So what exactly does this allow you as an exploit developer to do? Well, if you are lucky enough, depending on the code itself and how it's compiled, it could allow you to have a memory leak that will provide you with, for example, a randomized address of something from which you can calculate another relevant address that is therefore now known to you, and then use the second vulnerable printf to exploit the system while completely voiding the randomization protection. Let's see it in practice. If you look at the source code, right after the vulnerable printf, we have the string compare. Given the default GCC non-position independent option in this Ubuntu 1632-bit system, I can predict where to write to, which would be this address. Now I want to write the address of system there, so I can execute the bin sh shell. But I have 2 problems. One, we want this to work with ASLR enabled, which means we don't actually know where the address of systemlibc function will be at. And 2, it has to receive the sh string as a parameter in order to work and give me that shell. To figure out the system address, we are going to first disable ASLR, just to clearly see if we can find addresses dumped from the stack that are part of any specific memory regions when the executable is running. If we execute this, we can see that libc is in these B7E, B7F ranges. And if we dump the stack using format strings, we actually see, for example, this value, which belongs to the 3rd libc memory region. If we execute it multiple times, it's always the same value, which suggests it's pointing at something specific inside libc memory address space. Now, I must admit I had no idea what this pointed to, and it ended up in the stack completely by accident while I wrote the code. But the point I want to make is that in terms of exploiting this, we don't really care what exactly this is, as long as we understand it points to the same thing inside libc. But out of curiosity, we'll look into it at the end of this video. If you look at this dump, you can see that the different memory regions, all belonging to libc, are right next to each other in memory, and with the same sizes. What this means is that if we were to get the address, which we do, of anything inside any of these regions, we could basically calculate the addresses of anything inside it, including the system function. Remember the stack dumped address at position 2? If we go back to the libc addresses, we can see it belongs to this 3rd libc. But the one I'm interested in is the one where code is located, which is obviously the first one because that's the one with the X, as in executable. So given that we have an address in this 3rd libc memory region, all we have to do to get the executable libc baseline is subtract the offset of this memory address we dumped to equal the baseline of this 3rd memory region, then subtract the sizes of the others. But still, we need to add the offset of the system function relative to the libc, which we can easily get. And there you go. I can calculate the system function address even in an ASLR system. But I still have the second problem, which is how to provide the sh string to it as its parameter. This is also where we are lucky with the code, because both the printf and the string compare have the array buffer as their first parameters. String compare actually has 2, but swapping it with system function code pointer will have system only access the first parameter in stack and simply ignores the second parameter. We'll see the trick of how to do this while looking into the exploit code next. So let's see the exploit. Here we are using PwnTools, which is a Python module used a lot in exploit development because it helps us interact with command line applications. Usually, when it comes to CTFs and any exploit development tutorials, the code you're exploiting is often straightforward in terms of interaction, which kind of makes sense because you want to learn or practice the technique itself, and doing so doesn't usually require much code. But real applications can often require much more complex interaction for you to have good code coverage and to reach the vulnerable code. This is where PwnTools really helps. Now, in this specific code, Volno6, you cannot simply pipe in the payload. So we are going to use PwnTools because it's a two-way injection, if you will, which will require us to read the output from the first injection, then calculate some values and use this recalculation in the second injection. Exactly the kind of thing you would never be able to just pipe in. Also, keep in mind that this code is obviously very specific to the Volno6 application, as it is close to impossible to generate generic code here that you can just change a few variables, given that the output tends to be unique to each compiled application. Looking at this code, you can see two sections. The first, in which we read the dump of that second parameter from stack, and the second, which we are already familiar with from the previous videos, so don't require much explanation. Now, in this first section, we execute Volno6, then access memory address in direct parameter access2, then we wait for this line to show up and only then type in the payload. The final lines basically parse the output to retrieve the address, which we will present in the screen for debugging purposes. Having this memory address in the leak variable, we then proceed to calculate the what, which is the system function, by subtracting the offset to the third region in memory, and then the sizes of the second and first regions, and finally adding the offset of system inside that region. The where we already had from the GOT table. But what about the DPA? Before we get there, we need to understand how we are implementing, making sure the system function is getting the string sh in its first parameter, the only existing one from its point of view. As you can see here, we are starting the payload now with sh space and the pound sign, which, because this is a command line string, will basically comment anything that comes after, which is perfect for us. Another important detail here is the fact that this sh string has exactly 4 characters, which will be 4 bytes long. This is important to make sure the alignment in terms of direct parameter access is right. Remember that the index to which you refer to a position depends on the specifier you're using. If you're using %x, that's 4 bytes at a time. So if your value is in between, meaning partially in an index and the rest in another, you're just making your life more complicated than it needs to be. So if you are doing this in a 64-bit architecture, you definitely want to make this 8 characters long by simply adding whatever 4 characters after the pound sign. Also, keep in mind that if for whatever reason you cannot use the space character, semicolon here is just fine as well. Now, given that we injected 4 bytes in the beginning of our payload, as you might imagine, the direct parameter access will change as well. Given that the second printf could be somewhere else in the code, I definitely suggest having the second payload with a bunch of %access again and see exactly where would 4a's be if placed in the payload right after the sh initial 4 bytes. And after that, we pretty much just do the payload prep we've done in previous videos, and using PwnTools, send it out and interact with the shell that will hopefully retrieve. Let's see if it works. And there you go. But as you might recall, we're still in a disabled ASLR system. Let's fix that and see if this still works. It does. Awesome. ASLR bypassed due to a memory leak exploited with format strings. Now, one last thing. If you're curious like me, you must be wondering what was that pointer to libc we found in the stack. If you get into GDB and break at the vulnerable printf, we can see the stack value we dumped here. If you examine that pointer, GDB tells you what it is, standard input inside libc. If you look at the code push to stack, the parameters right before the gets function, we can confirm what it is. The third parameter out of 3 total is the first being pushed to the stack, which is this EAX register. If we look at what's placed in it, we can clearly see the standard input value. If this gets compiled for a 64-bit system, you won't be this lucky because if the function only has 3 parameters, they are just placed inside registers and not in stack. This third standard input would just be inside RDX, and we wouldn't be able to dump it from stack.